Now this is our first example about work and energy equations. In this example, what we have is a rotational joint right at this location. This is our location at point O. There's our rotational joint. And we have an assumption here that there's no friction force due to the rotation about this axis, or it is negligible. Other than that, the assumption is that the gravitational acceleration is in the vertically downward direction. And we have a beam and two spheres located at the ends of this beam. And another assumption is that this is a light beam or light rod, therefore its inertial properties are neglected. As a matter of fact, you can do these type of assumptions and then you can predict that it's a lump mass at the ends for such systems, but then you're neglecting some facts when you do these type of let me say assumptions. Therefore, this is again an engineering assumption. We have lumped masses here, 4 kilograms here and 2 kilograms here, and the moment arms with respect to this point O are different. And then this system of beam and then the spheres or particles start their motion at a theta angle, and the theta angle is given as 60 degrees and it starts from rest, which means that there is no initial velocity. The only force acting on the system, therefore, is due to gravity, gravitational force. Therefore, there will be a force here in this direction, okay? And this is 4 times the gravitational acceleration, or let's call it m1 times g. And then there's another force here, and then it's in the downward direction again. And this is m2 times g. And m2 is 2 kilograms. Okay. Until it gets to the spring point, which is the horizontal condition for this beam, there is no other force acting on the system. Therefore, if the only force acting on the system is the gravitational force, then we do not have any non-conservative forces acting on the system, because we already said that the friction is negligible, right? As a result of that, the total work done by the non-conservative forces will be equal to 0. And that tells us that the energy, the total energy in this system, is conserved. Or in another way of saying that, the change in the total energy is equal to 0. Remember, we had the equation that we discussed right over here. There's u prime 1 to 2, which is equal to the change of the total energy. And if the cause of this u prime, which is the non-conservative forces, is equal to 0, then this is equal to 0. The change in the total energy is equal to 0. Then the total energy of the system is preserved. So what we need to do is to calculate the total energy of the system at this initial instant and at the final instant. Now, at the initial instant, what happens is that the only energy in the system, because it's at rest, it's not moving, therefore it doesn't have any kinetic energy. It has potential energy due to the gravitation. As the spring doesn't have any effect until the third instant, we are talking about first and second instances, then the only source of energy that the system has is the potential energy. And now, in order to calculate potential energy, you're free to choose your frame, right? You need to choose a frame that makes sense. We know that at the end, at the second instant, this beam will be in the horizontal, and therefore probably it's a better choice to declare my reference frame to be located at this line, okay, at this line which goes through point O. Therefore, for this particle, we have this length h, 1, and then for the second particle, we have this, length h2.